Hello everybody, I'm back in OpenTTD. I thought that the crazy stuff is over, but it's not. Over here with the second version of Division, which I failed first time when I've done it, terribly. And then was the second version, which I made, it was working, but I was not satisfied, so I just published it and I didn't explain anything. Now, important thing is, before we start, that I'm going to explain only the things regarding Division. So I'm going to divide this video into two episodes. First, there will be a lot of theory on the diagrams. I will explain methods and then how the method is implemented in this circuit. However, everything on diagrams, and then I will confront the theory with reality, but without getting into details. All details will be in the next episode. And now, why I'm doing this way? Because I've got a feedback from my viewers, especially from Discord, who actually kind of, maybe not complain, but they say that it's difficult to follow me. And I guess my English is not the best, the pronunciation, the grammar, but I think the biggest problem is that I never explain some elements, like for example multiplexers and many others. Now, for all those who are watching my videos for the first time, the information about how to build display, how to select those segments, how to select the numbers for our operations, how to convert them to binary number, how to add them, they are all explained in other videos. So firstly, all those informations right now you can find in the first video about the adding in vanilla version of the game, so you need to check my channel. And then there was a separate video for this circuit, which is 2-in-1, adding and subtracting with the one module. Now, BCD converters, I never explained them thoroughly, but I mentioned quite a lot of information about this during video about calculator with 4 operations. The video is going to be very long, about something between 25 and 30 minutes. So let's start. Why I wanted to have a second version of Division? When I've done the first one, it was very big. It required 7 segments because I used 7-bit system. So it required 7 segments, one for each bit, to make those calculations. However, it was very fast. You could get the result immediately. But I wanted to have something smaller. Let's say that one segment that would be used for one bit, one after another. This circuit, this algorithm requires right now about 24 seconds, which is no bad comparing to my previous version of this version, because that was 2 minutes 30 seconds. Now there's a huge improvement, 24 seconds at the normal speed of the game, and about 5 seconds if I speed up the game. I expect you to understand how to make binary division by shift and subtract. If you don't know, just maybe you should look for it on internet before you go further. I want to explain this algorithm by doing an example, like over here, 14 divided by 4, and that equals 3 and 2/4. Now we will use the binary numbers, like over here, and it means that we need some kind of memory registers. So definitely we need something for dividend, something for divisor, something for quotient, remainder. As you can see, we have 2 blue registers, and that's because I decided to join them together. It means that at the beginning, actually, that blue register will be just dividend, then it will share dividend with quotient, and at the end it will be only quotient. This will become clear when we will doing our example. So now we need our blue register for dividend at the beginning. We're going to test the most significant bit, and when we will doing the next test, we will just shift that dividend 1 bit to the left. Now, as a human being, I don't need any leading zeros, but the computer needs that zeros. So we need to build additional register. I call it tested value. So right now we have a 1, and at initial stage, those 4 bits in brown rectangle, they will be set to 0. To make that test, I would have to build some kind of comparator, because we're testing if our divisor is smaller than the number in the green, the tested value. That means that I would have to build additional circuit. Instead of this, I can get the same result if I just subtract. So I need to have some kind of subtraction circuit, which is hardware, so I can't move it. So we need to be stationary. Our subtrahend over here will be our divisor, and the minuend will be always that tested value, copy from that green register. So now we're going to test our first bit of dividend, and it creates a number with the value 1. So we're going to subtract 1 minus 4 equals minus 3. This is negative test because the result is below 0. We cannot have a result below 0. It means that we cannot subtract. Now I'm looking for our quotient, and we need to have 0 because we didn't subtract. So if I change that most significant bit with a NOT gate, I will get 0, and that's our quotient. Now I'm putting that quotient on the right hand side of the blue register, and we're going, because we didn't subtract, we're going to just test the next bit. So we're shifting everything one bit to the left. So green rectangle, blue rectangle, and then value of the quotient. After I've done it, the blue register now contain 3 remaining bits of dividend and 1 quotient. Now the green register has a new value which stands for 3. Now we're going to test second bit of dividend, so we copy that green register into our minuend, and we have a new value over there. So we have 3 minus 4 equals minus 1. So again, we're not supposed to subtract. Most significant bit is changed with the NOT gate, and we get 0. That 0 is, again, I'm putting it on the right hand side of the blue register. Because we didn't subtract, we again just shifting everything one bit to the left. We're getting in the blue register now 2 bits of dividend, the 1 0, that's the dividend, and 2 bits of quotient, 0 0, that's quotient value so far. Now in the green we have new number, it stands for 7. We start testing our third bit, so we copy that blue register into minuend. We're subtracting 7 minus 4. Our difference is above 0. It means that we have over there 3. The most significant bit is 0. Now if I change that 0 with NOT gate, I'm getting 1. So that's my value for quotient. I'm putting that 1 on the right hand side next to blue register, and we're going to test another bit, but this time because we subtracted, we have a different action. Previously when our quotient was 0, we were just shifting everything, but this time we shifting only the blue register plus that 1 bit of quotient, and this time we replacing those 4 bits in the brown rectangle with the value of difference. And now we have a new values. In the blue register we have 1 bit dividend remaining and 3 bits of quotient. And now the green register stands for number 6. So we're going to test last bit of our dividend. We copy that 6 into our minuend register. In subtraction circuit, we subtract 6 minus 4 equals 2. Again, we have 0 as the most significant bit. We're changing it with a NOT gate and having 1. So I'm putting that 1 on the right hand side of the blue register. And again, we're shifting that blue register plus bit of quotient and replacing our 4 bits of that brown rectangle with our difference. And now we have our final result, which stands in the blue for full quotient, that's 3. And our brown register right now, it stands for our remainder 2. In case that we have our last quotient 0, we would not replace that brown rectangle, but instead of that we will just shift all those 3 elements, the green register, blue register, and the quotient 1 bit to the left. Our result will be like previously, a quotient in blue and remainder in brown rectangle. Now we start to explain how this method is implemented in my circuit. It would be much more difficult if we didn't explain this method before. Now, when you know the method, it's time to find a way how to put it into work. Now, I'm pretty sure that you recognize those 3 elements. Brown, that's the 4 bits that we set at initial stage to 0, and then depends on our subtraction result, we will or shift to the left or replace with a value of difference. The blue is our dividend quotient register. and that 0 on the right hand side of blue register is our current quotient value. As you can see, for the blue register we need 2 inputs, so we can select one of 2, and for the brown we need, let's say, 3 values, so we can select one of 3 values. And the easiest way to make such a selection is to build selectors, multiple input selectors. They actually are called multiplexers, but because I am not professional, I am a very uneducated person, so I think I'm off the hook and I don't have to call them multiplexers. I love the name multi-input selectors, and I will stay with this. Just multiplexers sounds to me very artificial and it doesn't tell me anything, but multi-input selectors is much more understandable for me as an educated person, so I will use those names. So those selectors need to have different inputs, so we have two kind of selectors. The blue, which requires 2 inputs, the dividend, and when we're shifting we need to have a value from the right hand side bit. And the brown, we need to set it to 0, we need to have a connection to our subtraction result, and as well when we're shifting we need to have a connection to right hand side bit. So it looks like this. And in additional, for the blue one, we need one line of control that will control what we want to do. For example, if it's initial stage, it is going to be 1 at the control, and that will tell the selector that I want to load dividend. And if it's 0 as a control, it will mean for that blue selector that I want to just shift that values. Now the brown is a bit more complicated because we have one selection out of 3. So we still need to have 2 inputs, so the difference and the bit on the right, that's 2. And then we need to have a control, 2 controls, because if you want to have 1 of 3, we need to have 2 controls. So one will be for initial state. When it's in initial stage, we will set those bits in brown register to 0. When it's not at initial stage, that selector will look into the most significant bit of difference, the result for our subtraction, and if it's 1, it means that our quotient is 0. It will just shift that brown register to the left. It means that it will look into bit to the right, and when is 0, that most significant bit, it means that our quotient is 1. It will replace the value in a brown register with the value of difference. That the second control is the most significant bit of that difference. Now, because still I want to explain in general, I don't want you to be disturbed by the design of selector itself, so we will not explain those selectors in this video. There will be good and thorough explanation in the next episode about this division, but otherwise that will be very long video, so I want to show you how to create such a selectors, and as well because we need to build those selectors and we have, let's say, less advanced players, so definitely I will have to talk about pre-signals, logic gates, and as well I will be talking about our memory registers, how they work, but that will be in the next video. The next step was to create something that will help me to shift those bits. One of the reasons I came back to this project, it was that I built a universal shift register in my 8 bits arithmetic logic unit, and I wanted to use something like this over here. But then I realized that if I don't use memory registers, those selectors on the top will changing frequently and I will get the wrong readings. So anyway, I had to use memories in order to lock the values. So instead of building additional circuit, I just built memory register and I connect them in a certain way that now is working very well as a shifter. So if you look at this, I call it auxiliary left shift register. It's exactly below those 2 blue and brown registers, but they are connected differently. So for example, the bottom register, the second bit, is connected to the first bit of the blue register on the top, and the third one is connected to the second on the top. the first bit on the right hand side, the less significant bit of that auxiliary left shift register, is connected to our quotient value. It's important to understand that this will work only when we get our subtraction result. So I will update this auxiliary left shift register only after we subtracted and we got our quotient result. Each bit of this auxiliary left shift register is connected to the selector above. Thanks to this, that this is a memory cell, and that memory cell is locked. The input to each of those selectors is stable. It will not change the value till the moment I want it to be changed. We're almost done over here. One more element. To make this circuit work, I need some kind of control. I built just a simple line along which the train travels at a certain speed, limited speed, and we have over here blocks that are connected to those elements. Not only they provide the right signal at the right moment, but as well they trigger updates of the memory cells of auxiliary left shift register, and as well they update the input memories to our subtraction circuit. So let's have a look how this is working from this side. Let's start, and we have a train in this block. When the train gets into this block, the signals over here will become red. It means that we have a 1, and we're sending a signal 1 to all those selectors. It means that we are at initial stage. When we are at initial stage, the blue selectors will have at its output the dividend, and the brown ones will have zeros. Yes, and now when the train is inside, it triggers I call memory update. At this time memory will be unlocked. It will get a new values into those brown and blue registers, and then still where the train is in this block, they will be locked. So before any other change will happen, we will already locked, and we will have zeros in the brown and in blue full dividend. Now there is a special connection. When we unlock the memory, the most significant bit of the brown register, it will trigger update of the input to the subtraction circuit. But this will happen only after we lock the main memory cells. That change will immediately change our subtraction result. We will have a new subtraction. That subtraction, the difference will be connected to those selectors, and they will immediately change them. But because we have our memory cell locked, nothing will change over here. We will still have the same values, despite the fact that our selectors already changed something. Now, after we've done it, we have our difference, and as well we have our quotient, because that's a very fast process, and the most significant bit of that difference is changed to opposites, so 0 to 1 and 1 to 0, and that's our quotient. And that quotient as well will be connected to the entry to that the less significant bit of auxiliary left shift register. It is not like it is on a screen. It will be just connected to that less significant bit of left shift register. At this moment, our train will leave the area when it indicates that this is initial stage. The train will move one block. One block will assure me that everything is set down. This is kind of free block. Our selectors will immediately change. It will provide wrong outputs, but nothing will change because we have a memory which are locked. Then our train will get into the block that will allow the auxiliary left shift register to be updated. We will shift all the values. So the blue and the brown will be shifted one position to the left, including the less significant bit as a quotient, and the memory will be locked. Now the train goes further. We are getting to the point where we're just updating memories with the new values from auxiliary left shift register according to most significant bit of difference. So if that bit is 1, it means that our difference is below 0, and the quotient is 0, it means that we want to just shift everything. So both brown and blue selectors will give us as output the values of auxiliary left shift register. When our most significant bit of difference is equal 0, it means that the difference is 0 or above 0, and it means that our quotient is 1. We will just shift only the blue register. So it means that the blue selectors as an output will give us a value of those auxiliary left shift register, the four bits on the right. The brown selectors as output will give us a value of a difference. So those 4 bits will be replaced with difference. When our memory will be locked, soon after our input to subtraction will be unlocked for a brief moment, and we will change the values of that subtraction as well with the quotient and so on. And that way we will testing all the bits. So actually I believe that this is the end of theoretical explanation. So first was method, and then how to make this method working in our circuit. Now it's time to confront theory with reality. Well, let me first identify the elements. The first we have that loop, programming loop, where the train goes along the straight line at a certain speed and makes the connections to the circuit that force this circuit to be updated at a certain time. Now the second thing is that we have over here selectors above the blue and red memory cells. Over here we have selectors for dividend and quotient, and above the green we have our selectors, the brown selectors from our example. Now those blue and red are memory cells for dividend quotient register. The green ones are actually from our example the brown one. Now if I add this red one to that green, we will get our green register with the tested value from our first example. Below we have yellow, red, yellow. That's our auxiliary left shift register. The less significant bit of it is our current quotient that is going to be, let's say, included in our shifting. Then we have our subtractor, which is actually not subtractor, and this is, I call it 2-in-1 module. It adds and subtract, so 2-in-1. And however it always adds, it works this way that it changing the subtrahend into, let's say, the negative value. So if we have a 4, it will change it to -4, and in this case, instead of subtracting, let's say 7 minus 4, we will get, we will do it is 7 plus -4. On the top we have the memory that locks the value to the input to the circuit, to subtracting. Now we have the visual difference over here, because I'm saying visual because the real connections actually go to our selectors above the green memory cells. Now the most significant bit of this difference is connected to the NOT gate. This is here, so green to red, so 0 to 1, and that's our quotient for this moment. So we waiting over here to with this to be updated. This is an old value over here. Now, so we're going to start our calculations. However, this is a difference. We have a 7-bit system. Our example was 4-bit system, so it's going to take a bit more time before we get our changes done. So let's unpause the game. We just getting into our initial stage. That initial stage actually firstly will influence the selectors, and then it will unlock the memory. So the memory are unlocked, so we are able to update those memories, and the blue and the red will be loaded with dividend, and the green one will be set to 0. That's initial stage. Now, as you can see, we unlock the memory. Our at the same time, our memory at the input to subtractor is still locked, but when we just get to about to lock, bam, so when the train just passed those blocking signals, it locked the memory, and now we at the same time we unlocking the memory at our subtractor. The result of subtraction changed, so now we have a minus, because that was 0 plus minus 4 equals minus 4, that's minus 4, and bam bam, so we got our difference changed. Most significant bit is 1 is changed with the NOT gate to 0, so we have this 0 here, and right now we are at the block that updates the left shift auxiliary register. So it right now it is updating that register, and again our train travels along and gets now to the next update for the memory. So we're updating the memory, we're shifting those things, and actually the first change will be seen when we get to the third, because that's actually, and now we should have difference, yeah, so that's the first one visible difference over here. So yeah, that's the way we're repeating the pattern, those actions one bit after another, and at the end we're getting to this moment where we actually, let's stop over here, we have some kind of separation register that separates the results from division circuit from the rest of the circuit, so it keeps stable the result display. Now when we get to this point, you will see that we just at this moment we unlocking this register, and that register allows the rest of the circuit to get the final result of our division. Okay, it's going to be the end. Maybe one more thing. If you look at this, if I speed up the game, let me speed up the game and pause the game. So if I speed up the game, it takes actually less than 4 seconds to calculate everything, the maximum speed of the game. Alright, so I hope that everything was understandable this time, and no details today. In the next episode I will explain how to calculate those selectors, two kinds of them, how to build them using pre-signals and logic gates, and as well I will explain the memory registers. So that's going to be another long video, I think within 2, maybe 3 weeks. I don't know how much time I can let's say put into it. So thank you for watching, and thank you for your likes, comments, and see you in the next episode. Bye bye.